Like, Hi, this is Jaydeep Sai, and the topic which I have selected for this TikTok video is reducing feedback delay of software development tools via continuous analysis. Abstract. During software development, the sooner a developer learns how code changes affects program analysis results, the more helpful that analysis is. Manually invoking an analysis may interrupt the developer's workflow or cause a delay before the developers learn the implications of the change. A better approach is continuous analysis tools that always provide up to date results. We present code based replication, a technique that uses the implementation of continuous analysis tools by converting an existing offline analysis into an IDE integrated continuous tool with two desirable properties, that is, isolation and currency. Codebase replication creates and keeps in sync a copy of the developer's code base. So during the software development, when the developer learns how code changes affect the program result analysis, the more helpful that analysis is. So, manually invoking an analysis may interrupt the developer's workflow or cause a delay before the developer learns the implications of the changes. So, while developing a code by the developer, if the analysis has to be performed, which is very necessary, then while doing it manually, it can cause a workflow interruption or can also cause delay in the work by the developer. So instead of doing manually, we can have the tools which can replace the manual testing or analysis. So we have presented a code-based replication, a technique that eases the implementation of continuous analysis tools by converting existing offline analysis into an ID integrated. So we can convert the offline analysis into IDE integrated continuous tool with two desirable properties. The code base replication has two properties, that is isolation and currency. Code base replication creates and keeps in sync a copy of the developer's code base. So while developing the code, the copy of the developer's code base can be stored and the sync can be done, or the backup or recovery of the code can be done. So the code can be tracked in the steps of the development. So let's discuss the introduction of the topic. When a developer edits source code, the sooner the developer learns the changes effects on the program analysis, the more helpful those analyses are. A delay can lead to wasted effort or confusion. 65365. Ideally, the developer work learns the implications of the change as soon as the change is made. So when the developer edits the source code, the sooner developer learns the changes. So while developing the code or editing the source code, the developer learns the changes. So the developer will store in the mind what the changes has been made, which affects the program analysis. The more helpful those analyses are, a delay can lead to wasted effort or confusion. So while editing the code and storing in the mind, it can make the delay, can lead to wasted effort or confusion. So the programmer may also forget or confused and wasted effort. So instead of making the changes in the mind, if it is stored in the computer itself, then it would be very useful for the developer and it will not have much effort to keep it in the mind what the changes have been made. And the time delay for the work can be reduced and the work can be done very easily and very early. Ideally, the developer learns the implications of the change as soon as the changes are made. Making an analysis continuous is challenging. This explains why few continuous analysis exist. Despite their benefits, two major challenges are isolation and currency. Isolation requires that one, the analysis should not prevent the developer from making new changes and code changes may be an impure. That is, side affecting analysis should not alter the code while the developer is working. And second one is developer edits should not make results of an ongoing analysis potentially stale. So here we can see the image. Here we have developers Eclipse. Eclipse is the IDE and background headless Eclipse display offline, run offline, and here developers editor, developer and edits action. So the developers editor will perform develop and edit actions on the core Eclipse plugins and developer edits and actions are performed on the Saltis server. So these actions and developer edits and actions are performed on analysis server and here the developer edits and actions are sent to background headless Eclipse. Here which runs offline. Here copy workspace. In this copy workspace, the changes which are made, the track of the changes which are made are stored in this copy workspace. And here in the Saltix client event queue. Here the changes are arranged in the queue fashion and develop edits and actions. These are stored in the offline analysis. Here the analysis client is present, which checks the what the changes have been made. And if the changes are okay, then resume the work or pause the work is performed. Replication. So let's discuss the key terms. Replication, keeping a separate in sync copy of the developer's code base on which the analysis executes. Buffer level synchronization, ensuring that the analysis has access to latest developer edits. And the third one is exclusive ownership. Exclusive ownership, allowing analysis to request exclusive right access to the copy of the developer's code base and staleness detection, identifying results made stable by new developer changes. So here we can see the table. Here the columns are analysis, A0 runtime, availability, average staleness. Here in the testing of the analysis, the runtime is 0.01 second and the availability of testing is 99.7%. So the testing is done very much here and staleness is 0.003. Here in the staleness detection, identify results made by stale by a new developer changes. So in the identifying the stale in the new developer changes, it takes 0.003 for testing and PMD runtime is 25 seconds and availability is 61.2 and average staleness is 10.9 seconds. And in the analysis of bug finding, that is find bugs, the average runtime is 74 seconds. So it takes 74 seconds to find the bug by using this technique. and availability is 33.7%, and average staleness is 108.6 seconds, and data race is 293 seconds for the runtime, and availability is 5.7%, and average staleness is 1124 seconds. So it takes a lot of average stillness time for data race, that is 1124 seconds. Definitions. Definition 1. Snapshot. Snapshot is a single developer's view of a program at a point in time, including the current contents of the unsaved editor buffers. A unique snapshot is associated to endpoint in time. Definition 2. Offline analysis. An offline analysis is an analysis that requires no human input during execution. So when in the snapshot is a single developer's view of the program at a point of time. So at the point of time, at that moment, the developer's view of a program is considered to be the snapshot, including the current contents of the unsaved editor buffers, and also the unsaved editor buffers are considered. A unique snapshot is associated to each point of time. Offline analysis is an analysis that requires no human input during execution. So in the offline analysis, no human input is required for the execution. Key design dimensions for a continuous analysis tool. Our approach to implementing the continuous analysis involves executing an offline analysis internally. This section discusses three key design dimensions for continuous analysis tools that are converted from their offline analysis. Triggering analysis execution. A continuous analysis may use four categories of triggers to start internal offline analysis execution. First one is whenever the snapshot changes in memory. Second one is whenever the snapshot changes on disk. And third one is periodically. And fourth is other triggers. Additionally, analysis from each of the categories may be delayed or and are overlapping. So this is about the triggering analysis execution. Acknowledgements. So this work was funded by the US National Science Foundation, which is NSF, grants CCF 09635757, CCF 10167001, and CCF 1446683. Hugspot worked on the marker visualization that was used in the case study. Isgi Merkan worked on an early stage of the Solstice prototype implementation. The authors thank Deepak Azad, Daniel Megret, and Stephen Herman for their help with the Eclipse internal throughout Solstice development. I thank the faculty and college for providing me this opportunity to speak on the selected topic. Thank you, Jai Hind.